In this video, we're going to start naming ionic compounds. So nomenclature. Nomenclature is just our fancy name for naming compounds. So ionic. We are also going to name covalently bonded compounds later on in this chapter. And our rules for naming covalent compounds are different than our rules for naming ionic compounds. So given a compound, you do need to be able to recognize, is it ionic or is it covalent? And we're going to use that guideline that our ionic compounds are usually between a metal and a non-metal. Watch out for polyatomic ions though, so between a metal and a non-metal, or involves a polyatomic ion. And then our covalently bonded molecules, compounds, will be between a non-metal and another non-metal. So kind of our guideline between a metal and a non-metal. Remember, our metal is going to be the one that typically loses the electrons, so it's going to become my cation. My non-metal is the one that typically gains the electrons, so it's going to become my anion. Or involves polyatomic ions. Polyatomic ions are a group of atoms that function collectively as an ion. So poly meaning essentially more than one. It technically means many, but we're not going to really have many, but we'll have more than one atoms. So polyatomic, more than one atom that functions as an ion. So an example, sulfate. I have sulfur bonded to 4 oxygens, and then that entire thing is going to have a -2 charge. So sulfur bonded to 4 oxygens, right? More than one atom functioning collectively as an ion. Because it's an ion, right? Because I have a charge here, it's going to form ionic bonds. So between a metal and a non-metal, between a cation and an anion, or involves polyatomic ions. In this case, because this has a negative charge, this would be my anion. So if you wanted to kind of narrow that down to just one sentence, or something simpler, you could say it's between a cation and an anion. So when we name them, we're always going to name the cation first, we're always going to name the anion second. And then if the metal is fixed charged, we're not going to have a Roman numeral. If the metal is variable charged, we are going to have a Roman numeral. So our first one, let's do fixed charged metals. So these are going to be our metals in group 1A, 2A. So group 1A metals, group 2A metals. And then also aluminum, which forms a 3+ charge, and then zinc, cadmium, and silver. So if it's a metal from group 1A of the periodic table, group 2A of the periodic table, aluminum, zinc, cadmium, or silver, it's going to fall into this category. If it's not one of these metals, then it's not going to be in this category. It's going to be under my variable charge metal. So by fixed charge, what I mean is every time these form an ion, they always have the same charge. So aluminum is always going to lose 3 electrons. It has 3 electrons that it needs to lose to have that filled valence shell, right? To have that octet, to have that stable noble gas electron configuration. My group 1A metals are actually all going to form a +1 charge. They have 1 valence shell electron that they're going to lose. We could just actually put a plus. So sodium, potassium, cesium, whatever metals are in group 1. Remember that hydrogen is a non-metal. And then group 2A, these guys have 2 valence electrons. They're going to lose both of those and have a +2 charge. So beryllium, strontium, any of the metals in group 2A. So every time sodium loses an electron, it's going to lose 1 electron, right? Not 2, not 3, it's always going to lose 1. So it's a fixed charge metal. So if it's in group 1, +1 charge. If it's in group 2, +2 charge. Be careful if I ask you why. It's not because it's in group 2, right? Remember, our periodic table is never our answer. Barium loses 2 electrons because it has 2 valence shell electrons, and once it loses those, it has that stable noble gas electron configuration, or an octet, or however you want to word it. So +1, +2. Aluminum happens to be in group 3A, so that's kind of an easy way to remember it. So if it's in group 1, its charge is going to be +1, group 2, +2. Aluminum's in group 3A, 13 if you're using the other naming method, but +3. And then I'm going to kind of sketch an ugly version of the periodic table, but this is kind of how I remember them. So I have group 1. Let's actually make it. So group 1, group 2. It is group 1 or 1A, 2 or 2A. Hydrogen is here. Again, hydrogen is a non-metal, so I'm going to ignore that. And then if we go over, this is not to scale because I'm ignoring my transition metals. Notice, I guess I'm not going to ignore all of them, but notice there's only these 3 that are transition metals in that list. I want to make this a little bit not quite so horribly and out of whack. There would be 10 here. Again, this is just kind of out of scale, but I just want to show a couple of them. If you have a periodic table in front of you, it's probably going to be more efficient to just look at it. But this is going to be group 3A. And this is where aluminum is. Oops, sorry, that's where, if you are looking at your periodic table, then you saw my mistake. That's where boron is. This is where aluminum is. Boron is a semi-metal, so we're ignoring that one. And then zinc is here. Cadmium is underneath it, which is actually why I drew it underneath it up here. And then silver is right here. So kind of how I remember these, and I know it's kind of weird, but if it helps, so group 1A, +1 charge, group 2A, +2 charge. Aluminum is in group 3A, so 3, and then it's a descending diagonal from aluminum. So if this is, aluminum again, if this is 3, this is 2, and then this is 1. So +3, 2, 1. So if you have your periodic table, which you're allowed to have on every test and quiz, you'll never not be able to have your periodic table. If you just remember aluminum in group 3, and then descending diagonal, 3, 2, 1. And then cadmium is in the same group as zinc, so it's going to have the same charge. So I just remember it's right underneath it. So if that helps you remember the order, right? If you were looking it up on your notes, you'd be cheating. So at some point, you do need to remember these. I didn't mean to, I just wanted to get those X's off of there. Okay, so back to naming. Fixed charge metals. So if it's in group 1A, 2A, it's aluminum, it's zinc, it's cadmium, or it's silver. When we name it, we're going to always do the cation first. So it's going to be the cation, and then it's going to be the anion. The cation is just going to be the name of the metal. So it's elemental name. So if it's silver, you say silver. If it's sodium, you say sodium. If it's aluminum, you just say aluminum. So elemental name. If you were just naming the ion, if it wasn't a compound, but if it was just zinc with a 2+, I would say it's a zinc ion because it's charged. We would say the word ion to differentiate between zinc with no charge, right? That would just be zinc. So zinc or a zinc ion. When we put the name together, though, to name a compound, because we're naming the entire compound here, right? Ionic compounds, is just going to be the elemental name. So if it's a zinc ion, we're just going to say zinc. And then the anion is going to be the elemental name, but, it's a big but, modified to include an IDE ending. So for the most part, it's just going to be the first syllable of the elemental name. We could actually do that, first syllable. And then it's going to be that modified IDE ending. So some examples. If I had oxygen, it's going to become ox and then IDE, so oxide. Nitrogen, what does nitrogen become, guys? Good, hopefully you said nitride. I'm not going to do all of them. Fluorine, what does fluorine become? I almost wrote it. Good, fluoride. Be careful when spelling fluorine and fluoride. The U actually comes before the O. It's a strange in the English language placement of those two letters. It's probably the most misspelt of all of our elements. So just be careful. The U does come before the O. I know I'm a horrible speller, but I did spell that correctly. Hydrogen. Hydrogen's a nonmetal. What does hydrogen become? This one, a lot of folks want to say hydroxide, if that's what you're thinking. You're not correct. Hydroxide is one of our polyatomic ions. What is hydrogen? Use our rule. First syllable, and then an IDE ending. Yeah, hydride. That's an R. So essentially, this is all we're doing. We're taking the elemental name of our metal, and then for our non-metal, right, our anion, we're taking the first syllable of its elemental name, but then we're adding IDE to the end of it. So for example, if I had CaCl2, so calcium is in group 2A, so it's fixed charged. I just said it's calcium. And then Cl is chlorine. Chlorine becomes chloride. So calcium chloride. How about Zn3N2? We will go in the other direction shortly, right? Remember, the number of electrons lost must be equal to the number of electrons gained. So my net charge in an ion compound always needs to be 0. So that's why those subscripts are there. But the name of it, I can just totally ignore those subscripts, right? If I go back up here and I look at how I'm going to name it, there's nothing mentioned about subscripts. So the elemental name of the cation, so zinc, and then I have it with nitrogen, which becomes nitride. So my name is really simply just that, zinc nitride. And that is 2 separate words. You do put a space between zinc and nitride, calcium and chloride. Let's do one more from this direction. How about Ki? So what is K? Good, potassium. And then I is iodine. What does iodine become? Yeah, iodide. So potassium iodide. So again, just the elemental name of the cation, right, of my metal. And then my non-metal, the elemental name, or the first syllabus, we should say, of the elemental name with that modified IDE ending. For variable charged metals, it's going to be very similar, except between the cation and the anion, I'm actually going to put a Roman numeral telling me the charge on that metal. So we did fixed charged. If it's a metal that's not fixed, it's going to be variable charged. So if you're given an ionic compound, so it has a metal and a non-metal in it, I'm going to have, or I should say a metal and a polyatomic ion, And the metal is not in group 1A, 2A. It's not aluminum, zinc, cadmium, or silver. It's then going to fall into this category. So number 2, variable charged metals. So it's just as it sounds. Some metals lose a different number of electrons when they form ions. We did an example earlier with iron. Sometimes iron loses 2 electrons. Sometimes iron loses 3 electrons. Right? I can't just look at the periodic table and say, well, it's in group 2, so that's how I'm going to remember how many electrons it loses, right? So we have to, in the name, say what type of iron it is. Like back up here, calcium is always going to be +2. It's never going to be anything other than +2. So if it's an ionic compound, I know it's an ion, so I know it has a +2 charge because I'm saying the word calcium. Zinc is also always going to be +2. Potassium is always going to be +1. So I don't have to differentiate. There isn't another option for potassium. But for iron, I have options, so I need to say which one. If I just say iron oxide, which iron am I talking about, +2 or +3? So when we do this one, we're going to have the cation, and then I'm going to have a Roman numeral that indicates the charge on the metal, right, on the cation. And it's important that it's the charge. A lot of folks will go wrong on this. It's not the number of them that I have, it's the charge. So Roman numeral that indicates the charge on the metal, and then the anion, this still has that modified IDE ending. So the only thing that we've changed here from fixed charge metals is that Roman numeral. So that Roman numeral again is giving me the charge on that metal. Before we do some examples, I do want to look at the charge on my anions first. The way we're going to figure out our charge on our cation is we're going to remember that our net charge needs to equal 0 for ionic compounds, right? The number of electrons that that metal is going to lose is going to be equal to the number of electrons that my nonmetal is going to gain. So we don't know the charge on our cation, right? For example, if I was to write FeCl3, because this is variable charged, I don't know what it is, but I do know the charge on chlorine, right? When chlorine becomes chloride, right, when it gains that electron, it's going to gain 1 electron. I happen to have 3 of those, right? That's what this subscript tells me. I know my net charge has to equal 0, which means iron is going to have a +3 charge. So the name of this compound is iron 3 chloride. If I didn't know the charge on chloride though, right, if I didn't know that that was a -1, then I wouldn't have been able to determine that that was a +3, right? I can't just look at the periodic table and get the charges for these because they're variable charged, right? Sometimes iron is a +2. So we do need to know the charges on those anions. And we were looking at these earlier. Remember, the number of electrons that it gains is the number of electrons that it needs to gain to have either that octet, you could say a stable noble gas electron configuration, to fill up. They're not going to actually all have filled valence shells, only only the things in the second period, but you could say to have an octet in the valence shell. So just kind of, let's make a little periodic table. I'm going to look at group 5A. So our first one here is going to be nitrogen. We'll look at group 6A. So oxygen, and then group 7A, so fluorine. The reason I'm not including carbon is that carbon tends to not form ionic compounds. It could. It has 4 valence electrons right now, and it could gain 4 to get its octet, right, to have the same electron configuration as neon. But it also tends to lose electrons. So carbon, again, just generally doesn't form ionic compounds, so I'm not going to include it in this list. So I'm starting with nitrogen as I go across period 2, right? We're not including boron because it's a semi-metal. Beryllium and lithium are metals. Remember, my non-metals, sorry, I'm getting tongue-tied, are the ones that tend to gain electrons. I'm not including my noble gases, 8A, because they tend to not form compounds. Xeon actually does, but it forms covalent compounds and only with fluorine. So I'm really just looking at these 3 groups. And if I was to look at nitrogen, and I was to draw out its valence shell electron configuration, so I'm just doing my outermost shell, I have 2s2, 2p3. So to get, right, it has 5 electrons right now, 5 valence shell electrons. So to get its octet, it's going to gain 3 more, so it's going to have a -3 charge. Under nitrogen, I have phosphorus, and if I was to draw its electron configuration for the valence shell, all I'm going to do is change those 2s to 3s. Elements in the same group are going to have the same valence shell electron configuration. It's just that that valence shell happens to be different. So in nitrogen, my outermost electrons are in the second shell. In phosphorus, it's in the third shell. But they both have 5 electrons in their valence shell. It wants 8, right? It wants an octet, so it's also going to gain 3 electrons. Kind of a shortcut if we look, right? I said it has 5 valence electrons, right? 2 there, 3 there. So 5 valence electrons, it happens to be in group 5. Now, it doesn't have 5 valence electrons because it's in group 5, right? Watch out for backwards logic, but this is how we're going to remember it. So if my non-metal is in group 5, I'm going to say it has 5 valence electrons, it needs 3 more, so it's going to have a -3 charge. If I look at oxygen, and I'm just drawing the valence shell configuration again, so 2s2, 2p4, I have 6 valence electrons. It needs 2 more, so a -2 charge. Sulfur, again, is in the same group, so all I'm doing is I'm changing my valence shell from 2 to 3, but the configuration is going to be the same. Again, I have 6 valence shell electrons. It needs 2 more to have the octet. Selenium, right? If I was to add that one, 4s2, 4p4 needs 2 electrons. So again, those have 6 valence electrons, 2 here and 4 here. It happens to be in group 6. So if you were to take 6, subtract it from 8, I need 2 more electrons. For the things in group 5, take 5, subtract it from 8, 3 more electrons. Using that logic, group 7A, 7 subtracted from 8, 1 more electron. If you were to draw the electron configuration for it, and again, I'm just doing valence shell, I have 7 valence electrons, right? 2 here and 5 here, so that's 7. It needs 1 more to have that octet, so -1 charge. If you wanted to do chlorine, change those 2s to 3s, right? If I wanted to do bromine, change those 3s to 4s. No matter how you do it, right? If I want iodine, change those 4s to 5s, I'm going to have 7 valence electrons. I need 1 more to get an octet. Hydrogen is a nonmetal. Don't forget hydrogen. Hydrogen has, if we draw its electron configuration, 1s1. Remember, in the first shell, I can only have 2 electrons maximum, so hydrogen only wants 1 more electron, so it's going to have a -1 charge. And this is essentially all of our nonmetals. We're not going to really have anything other than this list. So use the periodic table again as your tool to help you remember it, right? This has 5 valence electrons, not because it's in 5, but it is in 5, so we'll use that to help us remember it. It wants 8, so it needs 3 more. These guys have 6, it wants 8, so it needs 2 more. These have 7, it wants 8, so it needs 1 more. Hydrogen, right? It has 1, it wants 2, so it's going to gain 1 more. So based on these charges, we can then figure out the charge on our metals. So nickel, I don't want to tell you the name, sorry, Ni3N, I almost gave it away. So Ni is nickel, I just told you that one. Sometimes nickel, both its spellings are acceptable. If you put EL or LE, either one's fine. Honestly, I'd use both. There's really no rhyme or reason to which version I use. Kind of looks cooler the second way, so let's do that. And then I do need my charge in parentheses. So what's my charge on nitrogen when it's an ion? So what's my charge on nitride, I should say? Go back up. Yeah, nitrogen's in group 5A, so that's how we're going to remember that it has 5 valence electrons. So it's going to have a -3 charge. This 3 tells me I have 3 nickels. So what's my charge on nickel? So when I add it together and then add it to my charge on nitrogen, it sums to 0. These are all going to be a +1, right? If they're all a +1, then I have a 3+ total. 3+ and 3- is equal to 0. So nickel 1 nitride, right? Nitrogen becomes nitride. Again, be careful. That Roman numeral is the charge. It's really tempting to see the 3 up here in the formula and put a 3 in parentheses. But remember, what goes in parentheses is the charge, not the number of atoms that I have. So all of the examples we've done so far have been for binary ionic compounds. So both the fixed and variable charged metal examples we've done, binary means 2. So ionic compounds that contain 2 different elements. They can have more than 2 atoms, but there's 2 different elements. So if I go back and look, here I have nickel and nitrogen. I actually have 4 atoms total, right? Because I have 3 nickel and 1 nitrogen. So that's 4 atoms, but 2 types of atoms, right? Nickel atoms and nitrogen atoms, so considered binary. If we go up to iron 3 chloride, sorry, right, variable charged metal, I do need that Roman numeral. So again, just 2 different types of atoms, and then all these examples also. More than 2 atoms total, right? The zinc here has 5 total atoms. This has 3 total atoms, but 2 types of atoms, right? Atoms of 2 different elements, so binary ionic compounds. I do want to do some with polyatomic ions next. And I've talked about polyatomic ions a few times. So these are groups of atoms that function collectively as an ion. And I have mentioned also in the past that there's a big list that you need to memorize. So I am going to go out a minute and show you that list. They are posted on Canvas for you. An example real quick, I think I used sulfate earlier, so let's do ammonium. So nitrogen bonded to 4 hydrogen, and then that entire group is going to function as an ion. So it's going to have a positive charge in this case. So I'm going to go out. These 2 handouts, I'm going to show you 2 of them, are both posted on Canvas. So this first one are the ones you need to memorize. So if I make it a little bit bigger here so we can read. These are the polyatomic ions that you are going to be expected to know. If you've had Chemistry 130, some of these should be familiar, but you never really had to memorize them because they are on the front of your periodic table. This time they are not on your periodic table. Using this sheet on tests and quizzes would be considered cheating, so I do expect you to learn these. So you need to learn the formula, the name, and the charge, right? If I give you ammonium chloride, we need to know what ammonium looks like. And if I say NH4Cl, we need to be able to write that, write the name as ammonium chloride. So please do spend some time memorizing these. In addition to this list, if I go back out, and this is also posted on Canvas, we have a list of rules for naming other polyatomic ions other than ones that are on that memorized list. So you also need to learn these rules. So please put some time into learning this. You are going to be expected to know them. And we're going to use some of them in some examples next. So for polyatomic ions, essentially we're going to do the same way, because we're still under ionic, right? If it's a polyatomic ion, right, it's a charged particle, they form ionic bonds. So I'm still always going to have my cation first. So if my polyatomic ion was ammonium, it's actually going to go first because it's my cation. If sulfate, which is SO4 2-, was my polyatomic ion, then that's actually going to go last because it's an anion. So it's still always going to be cation first. It's still always going to be anion second. Every time we name a polyatomic ion, it's always going to be cation first, and then, anytime we name an ionic compound, it's always going to be cation first and anion second. And then I'm going to make like a kind of a way to name our ionic compounds that's going to work for variable charged, fixed charged, and binary or polyatomic ions. So the cation, if a metal, right? So if it's a metal ion, simply state the elemental name of the metal. So this is, I guess, option 1. Option number 2, if a polyatomic ion, simply state the name of the polyatomic ion. And then I'm going to move anion over because we need to put some parentheses in here. We're going to have a Roman numeral indicating the charge on the metal if, quadruple underlined, it's a variable charge metal. So if it's not a metal from group 1A or 2A, aluminum, zinc, cadmium, or silver, and it's a metal, you're going to need that polyatomic ion, or Roman numeral. I don't know why I keep saying polyatomic ion, sorry guys. So our cation, if it's just a metal, just say the name of the element. So if it's sodium, say sodium. If it's iron, say iron. If it's a polyatomic ion, just whatever the name of it is. So this here is ammonium. If that's what my cation is, I'm just going to write ammonium. Next, I'm going to have a Roman numeral that tells me the charge on the metal, but only if it's a variable charge metal. If it's fixed charge, I'm not going to have it. If it's a polyatomic ion, I'm not going to have it. So I'm only going to have that Roman numeral if my metal is a variable charge metal. The easiest way to learn those is to remember the fixed charge metals. If it's not one of those, it's variable charged. And then for my anion, I'm going to have 2 options for this one too. If a nonmetal, you're going to modify the elemental name to end in IDE. So that's where you're taking the first syllable and then you're adding IDE to the end of it. So sulfur becomes sulfide, hydrogen becomes hydride, chlorine becomes chloride. And then number 2, if a polyatomic ion, simply state the name of that polyatomic ion. So if it's hydroxide, just say hydroxide. Okay? If it's sulfate, say sulfate, whatever that polyatomic ion is. And this should get us naming all of our ionic compounds that I'm going to give us. Again, you do need to learn those polyatomic ions though. If I say acetate, you need to know what acetate is. So please spend some time learning those. The 2 handouts are posted on Canvas under the handout, the practice problem and handout module. So I'm going to go through some examples. We've done examples of fixed charge and variable charge ones already, but I want to do some with polyatomic ions. I want to mix them up so you kind of know, you get some practice knowing what category they're in. And then also, we want to go in both directions. So given the formula, be able to write the name, but then also given the name, be able to write the formula. So I'm just going to start jumping in with a whole bunch of examples for us. So our first one, let's do CaOH2. So right away, I know that this isn't a binary one, right? This is one that includes a polyatomic ion because I have 3 different atoms. I have calcium, I have oxygen, and I have hydrogen. And OH with a negative charge is hydroxide. And again, I won't be telling you that. I am now because you haven't probably learned them yet. But you will need to know that because we can't name this if you don't know what it's named, right? Ca is calcium. And is calcium a fixed charge metal or a variable charge metal? Good, it's in group 2A, so it's fixed charged. If you weren't sure, just find it on the periodic table, right? If it's in group 1A or 2A, it's gonna be fixed charged, and then you did need to remember those other ones, right? Aluminum, zinc, cadmium, and silver. So if it's a group 1A metal, a group 2A metal, or one of those, it's going to be fixed charged. If it's a metal that's not one of those, it's going to be variable charged. So calcium's a group 2A, it's fixed. Because it's fixed, I'm not going to need that Roman numeral. So calcium hydroxide. Right? If my anion is a polyatomic ion, that's this part, I'm just going to state that polyatomic ion. So calcium hydroxide. Let's do CR NO2. So what is CR? So CR is chromium. And is it fixed charged or variable charged? If you're thinking variable, you're correct. So I do need Roman numerals. And remember, the Roman numeral is going to come from the charge on that metal, and we're going to figure out the charge on the metal based on the charge on my anion. So NO2 is one of our polyatomic ions. It has a -1 charge, and its name is nitrite. So since NO2 has a -1 charge, and I only have one of them for one chromium, that means that chromium must have a +1 charge. So 1 is going to go into those parentheses, and then nitrite, right? If it's a polyatomic ion for my anion, I just state the name of that polyatomic ion. So chromium 1 nitrite. Do note that I have parentheses around hydroxide here. I don't have parentheses around my nitrite. I could, it's not wrong if I do, I just don't need them if I only have one of them. So I have 1 chromium and 1 nitrite. If you have more than 1 polyatomic ion, like in calcium hydroxide, right? I have 2 hydroxides for every 1 calcium, right? Calcium has a +2 charge, right? It has 2 valence electrons I'm going to lose. So I have 2 hydroxide for every 1 calcium. Anytime you have more than 1 of your polyatomic ion, then you have to have those parentheses. If I was to get rid of them, it looks like I have 1 calcium and 1 oxygen and then 2 hydrogen, right? That's what that would look like if I got rid of those parentheses. I don't have that. What I have is I have 2 hydroxides. So anytime you have more than 1 of your polyatomic ion and you're writing your chemical formula, you have to have parentheses. If you only have 1, like my chromium 1 nitrite example, you don't have to put them there. I do need the nitrogen, however. You don't have to put it there. It's not wrong if you do. It's okay to put the parentheses there. You just don't have to. So in these two examples, I would have to have them for calcium hydroxide. I do not need parentheses for chromium 1 nitrate. So let's do an example going in the other direction. So tin 4 sulfide. So when we're going in the opposite direction, right, when I give you the name and we have to write the formula, we need to figure out what those subscripts are. And remember, our net charge on our ionic compounds has to equal 0. So what I need to do is I need to figure out the proportion of each that I need. So when I add them together, it sums to 0. So my symbol for tin is SN. And then remember, this Roman numeral tells me the charge. So I have a Roman numeral 4, so tin has a +4 charge. Sulfur is what sulfide is once it gains 2 electrons. Be really careful, really careful. This is a common mistake. SO4 2 minus, SO3 2 minus. Those are 2 polyatomic ions. This is sulfate. This is sulfite, ITE. And then sulfur is sulfide, right? The first syllable of its elemental name followed with IDE. So just be really careful not to get sulfate, sulfite, and sulfide mixed up. Another common one, here I have nitrite. Nitride, IDE, is nitrogen, right? So if nitrogen gains 3 electrons to get its octet, it's now a nitride ion. So just be really careful. There's only a 1-letter difference between nitrite and nitride, but they're totally different, right? One is a polyatomic ion. The other is just an ion, just a single ion, right? It's an atom that has gained electrons. So just be really careful to not get those guys mixed up. It's super easy to do that. So tin 4 sulfide. I have tin with a +4 charge. I know that again because that's what that Roman numeral is telling me. And then sulfur is in group 6 of the periodic table. Remember, we're using that as our shortcut to remember how many valence electrons it has. So it has 6. It wants 8 in its valence shell, right? It wants an octet, so it's going to gain 2 more, so a -2 charge. Then our question is, remember, our net charges have to be equal to 0. If this is a +4 and this is a -2, how many of each do I need so that way my net charge is 0? Yeah, I need 2 sulfides, right? Now I have a -4 total, a +4, that adds to 0. So my formula is SnS2. So that would be the correct answer. There is a shortcut that you may have learned, and I'm fine with you using it. You just have to be really careful. And the shortcut is that the charge on your cation becomes the subscript on your anion, and then your charge on your anion becomes a subscript on your cation. But remember, when we were talking about empirical formulas, I had said that ionic compounds are always empirical. So in this case, if you did that shortcut, you actually have to reduce it. So the shortcut, basically, I would take, I'm just going to rewrite them here. I would take tin with its +4 charge, sulfur with its -2 charge, and then this 4 is going to come over, and this 2 is going to come over. And then I would have SN2, S4. The problem is this is not empirical, right? I can reduce it. They're both divisible by 2. And if you don't reduce it, it's actually incorrect. So SnS2 is my answer, right? The reason, right, is that we don't crisscross, and that's just a shortcut, right? The idea is our net charge has to be equal to 0. So if tin is going to lose 4 electrons, 1 sulfur is going to gain 2 electrons. I need 2 sulfur for every 1 tin. The crisscross is just a shortcut. So if you want to use the shortcut, that's fine. Just be really careful if you reduce it. If you're going backwards, right? If I give you SnS2 and you're going backwards, it's really tempting to put a 2 for the Roman numeral for tin, but it's not. It's a 4. So just be really careful anytime you take shortcuts. right? If we want to look at the shortcuts for these other ones, just so you can kind of see how it works. Looking at the nickel 1 nitride, nickel, right, has a +1 charge, nitrogen has a -3 charge. So if we do that crisscross thing, I end up with Ni3N. I can't reduce it, so I'm fine, right? Just always look to make sure that it can't be reduced. If it can be, make sure you reduce it. Ionic compounds are always empirical. Let's do another example from that direction. So ammonium sulfate. So both of these are actually polyatomic ions. And I'm going to do the same thing that we did with the last one. I'm going to write their formulas. So ammonium is nitrogen bonded to 4 hydrogen, and it has a +1 charge. Sulfate is also a polyatomic ion. It's sulfur bonded to 4 oxygen, and it has a -2 charge. So then our question is, how many of each do we need to make our net charge equal to 0? If this is +1 and this is -2, I'm going to need 2 ammonium for every 1 sulfate. So NH4, and then remember, anytime you have more than one of a polyatomic ion, you need those parentheses. Right? If I didn't have them there, it would look like 1 nitrogen and I guess 42 hydrogen, which would be completely wrong. So you have to have those parentheses. I only need 1 sulfate, so I don't need parentheses around that one. If you wanted to put them there, it's not incorrect. It's just not necessary. Your shortcut would work for this if you want to use it. Right? This 2 is going to come over, so that's that 2. And then the 1 is going to come over, and you don't have to show the 1. Just always make sure that it can't be reduced. And if it can be reduced, make sure you reduce it. Let's do one more example. Let's actually go in the forward direction this time. So CO, and then ClO3, and then a 3. So ClO3 again is another polyatomic ion. So we're gonna have to look at that. CO, what is that one? Good, cobalt. Fixed charged or variable charged? Okay, variable charged, it's a transition metal, and it's not zinc, silver, cadmium, or what am I missing from that? I guess just those 3 that are transition metals. So I do need a Roman numeral, so we're gonna need to get that based on whatever the charge on my anion is. So ClO3 has a -1 charge, and the name of it is chlorate. So since it has a -1 charge, and then this subscript tells me I have 3 of them, what is my charge on cobalt? So that when I add all that together, it sums to 0. Good, hopefully you're saying 3. So I'm going to put 3 in parentheses, and then chlorate. We'll squish it in here. Hopefully I won't run out of room. So cobalt 3 chlorate.